Okay, so again, organization of muscle. We have the belly of the muscle surrounded with epimysium. Okay, and then the belly is made up of several different fascicles, and each fascicle is going to be surrounded with perimysium. Then we see each fascicle is made up of fibers, and each of these fibers is going to be surrounded with endomysium. Okay, now fiber, muscle for muscle, muscle fiber is synonymous with muscle cell. So when I say muscle cell, I'm also saying muscle fiber. Okay. And again, this is not relevant too much at the moment. We spend a lot of time on the cellular level next semester when we analyze function. Okay. So we're going to stop at that point regarding you definitely need to know this for this semester. The next little thing I just want to mention for the future is the muscle fibers then are going to be each, so we can pull out one muscle fiber, bring it down here. And notice you can even see up here, each muscle fiber is made up of bundles of more items we call little fibers or fibril. Usually if I put an IL or an ELL or an IOLE on the end of something, it means little, whatever it is. So a fibril is a little fiber. Myo again means muscle. So each one of these muscle fibers, which again is a muscle cell. So what would this endomysium, and again, this is just kind of thinking about cells, okay? When we look at this muscle fiber or muscle cell, we called this layer around it the endomysium. We could also possibly call that the cell membrane, even, right? The endomysium is what surrounds a muscle fiber, and a muscle fiber is a muscle cell. It's a distinct, odd looking cell, but it is a muscle cell. And each of these muscle fibers or muscle cells, notice it has multi-nucleated features. This is a nucleus, this is a nucleus, this is a nucleus. So anyway, we can also see mitochondria represented in the bottom here, but notice these are myofibrils that then make up a muscle fiber. It doesn't end there. For us, it ended a long time ago, but I can't stop. And there's another F word, so probably shouldn't have started recording. This might get YouTube dinged for all the F words, but these are called filaments. The smallest unit is a filament. So we have filaments, fibrils, fibers, fascicles. Yeah, there you go. Okay, we're not going to worry about the fiber on down. Okay, we're stopping at fiber. Okay, so again, three things. Okay, we're going to go from deep to superficial. So the deepest is the endomysium around each fiber. Then we had perimysium around each fascicle. And then we had epimysium, epi meaning upon the entire belly. You guys see that? So muscles just bundles upon bundles upon bundles upon bundles of protein strands. The smallest strands are called filaments. And then we bundle filaments and have fibrils. Then we bundle fibrils and have fibers. We bundle fibers and have fascicles. Then we bundle fascicles. And finally, we have a muscle belly. So that's a lot of action. And all of that physiological stuff to get my muscle to do this and to get me to be doing all of this and yap, 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 just even blinking your eyeballs or blinking your eyelids, or blink your eyeballs, that'd be weird, but blink your eyelids. So all of that is muscle. Okay, that's all epimysium, perimysium, endomysium, all the way down to the filament level where we have these little ore blades connecting with these little twisted pearl looking DNA fiber strands of protein sliding together and creating large scale movements. When I first started taking A&P many years ago, 1992 was my first A&P class. They called that the sliding filament theory, and it's progressed enough with electron microscopes, and it's now generally thought of as a law. It's now just the sliding filament mechanism. So in case you're wondering, how the heck would they know that something that's so small is doing and making that action? Electron microscopes, big microscopes, give us small images. Lori, we'll talk. That's getting. We'll talk about that later. I don't want to put you off, but that's going to take. That gets us into some cellular stuff that I don't really know if anybody's ready for. But in advance, you have a case study on ALS and a few other neurological items that gets into some of the nuts and bolts of what's going on at that level, at that filament level, with what we call troponin, tropomyosin. We have what are called the sarcoplasmic reticula that dump calcium, and there's to get the heads to unbind, we need ATP. And in order to get all this to happen, we have to go back to the nervous aspect, what's called acetylcholine. And acetylcholine is a neurotransmitter that basically starts the domino effect to get muscles to contract. And then we have to uptake acetylcholine. It's called acetylcholine ACE, what they call acetylcholine esterase, which is an enzyme that pulls acetylcholine back to get the muscle to relax. So that's where a lot of the problems lie with the enzymatic activity.
I have a friend whose mom is in the later stages of ALS, and she's starting to notice, like, she thinks that she has to clear her throat a lot. She's having issues with small muscle breathing. So she keeps asking me questions, and I said, it has to do with all those very tiny muscle fibers. But to try to explain
you
that, it's hard.
It is hard, but it's that. So the fiber level is the cellular level. That's where the mitochondria will be inside of there. That's where we call it the sarcoplasmic reticulum. And you guys remember endoplasmic reticulum, the network of tubes. And sarco means flesh. So we see sarcoplasmic, it means muscle. Sarcoplasmic reticulum, that's where the calcium is stored. That gets triggered and released inside of the fiber, and then that triggers deeper work in the filament level that are actually going to cause the connection. And between each connection and detach, that's where ATP comes in. And again, if we don't have enough, it gets into like rigor mortis even too, like, yeah. That the tension, but yeah, ALS, that's rough. I mean, that I had a student whose grandfather had ALS, and he lived in Madison in a nursing home, and he had been diagnosed with ALS like in the early 60s, and he still was alive in the early 2000s. He lived with ALS for like 40 some years. It was like medical record books. And I think some folks thought that maybe he was maybe misdiagnosed or something, like he had something. But anyway, it eventually goes after your diaphragm, right? And once it really, then respiration shuts down, and but yeah, muscles become flaccid in areas, because there is tone to muscle all the time. We'll talk a little, well, kind of now is kind of segueing into like tone. There's always a little bit of tonicity to muscle, even when they're relaxed. It's part of that proprioception. It's part of posture. It's part of keeping like your hyoid bone in place so your trachea stays open, keeping your diaphragm so it doesn't have to completely relax and then completely contract every single time you breathe, right? So there's just like with your posture muscles, there's always something going on. With ALS, the acetylcholine dump and the acetylcholinesterase, so the acetylcholine gets dumped, I get the muscle contraction, and then the acetylcholinesterase takes over, and then it keeps taking over, and it'll actually block acetylcholine release. And so then you start getting muscles that just aren't getting neurotransmitters dumped to enable calcium to be released and connections to occur. That's a tough one. That one, they haven't really been able to figure out, unfortunately. And they don't know how it happens. Okay. Um, so yeah, nervous system plays a role in everything. So is it brain related? Is it neurotransmitter? Because it's systemic, it's got to be something all the way up, I would imagine, uh, in the central nervous system. Okay, so muscle contraction type. So we went through uh, the connective tissue components. Now, different types of contractions. We really just see two main types. We see what's called isometric versus isotonic. The isotonic contraction is generally how you guys want to approach it is going to involve a range of motion. So we're going to see, by the way, uh, this again is introductory to some bigger picture stuff that we deal with in advance. We're going to talk in advance. We do a lab even called that goes through what we call the length tension relationship. So we'll do, I know we actually do a little bit of math. We do a little bit of algebra when we're figuring out some of the physiological aspects. So you do have that to look forward to next semester. Length tension relationship. You're hearing it now. You're going to hear it in more detail later. But in essence, what we see with isotope, so there, first of all, there's a relationship between the length of the muscle fibers. Are they elongated and stretched, or are they shortened and performing an action? So that's length. And then tension is how much stress or strain or how much weight, what is the load that we're dealing with? How much tension? Okay, that's in essence, that's the load that we're trying to move. So when we look at a muscle that is going through an isotonic contraction, we see that as having some sort of motion. There's range of motion. The length of the muscle changes. Okay. Tension. Um, Oops. So I'll go back. I've got a couple things to show. So I'm going to kind of be going back and forth. But we see with isotonic changing length. Okay. So there's movement, there's a range of motion. The tension doesn't change. Though, in other words, the the weight of the ball is 5 pounds out here. The tension it's putting on my muscle is 5 pounds of tension. As I lift and shorten, I'm changing the length. It's still 5 pounds of weight. And that initial, that action, the what we call the primary movement or primary action in an isotonic contraction is also called a concentric movement. Concentric. So you're going with the center. Okay. So concentric movement, you can see this is a bicep curl. So he's going from somewhere down here and he's bringing the dumbbell up towards his. So he is performing flexion of the elbow, the biceps the biceps brachii and the brachialis muscles of the anterior part of the arm are shortening. We're seeing the fibers shorten. We're seeing contraction. We're seeing range of motion. Okay, that's called concentric. Now, when he's ready to put the dumbbell back down, okay, is he going through a range of motion? Yes, right? So it's got to be an isotonic contraction, but he's no longer going through the original range of motion. He's going through a different process where we're seeing the original muscle that was shortening. We're now seeing that prime mover, the bicep, the fibers are going to start lengthening, but we're still performing that we still see shortening of muscles. This time, it doesn't show it on there, but this time the triceps are actually shortening while the bicep muscle is lengthening as he puts, we call this then elbow extension. So as he's moving the dumbbell back down, we're going to see, again, some muscle contraction, but this time the contraction is going to be in the back of the arm, and the elongation or the stretching is occurring with the bicep. Now, that's called an eccentric, or it looks like eccentric, which is fine. It's probably, but we usually think of eccentric as being a personality trait. So they, in biomechanics or kinesiology, physical therapy, they say eccentric and concentric. So anyway, concentric is the prime movement to perform the action. Eccentric is going back to the original spot where you were. And again, the emphasis too is that once I get to this spot and I go back to where I started, I don't just let go of the weights. Is kind of what it's trying to imply. Like an eccentric contraction still involves some sort of shortening and some use of muscle. We're not relaxing the entire complex. Okay, at least you shouldn't. That could cause a problem, especially if you're moving something, right? You don't lift up a glass of milk or water, and then once you're done, it just flops down, right? You have to control that. We call that reverse action. Okay, so when you're going back, we call that reverse action. Okay, eccentric movement. So both of those are isotonic. We see a change in length. We don't see much in the way of a change in tension. The next one is called isometric. Isometric, there's no change in length. So this is like pushing up against a brick wall. Or this is like if you go to lift something up, it's too heavy and nothing happens. You still feel some muscle tension, right? There's still tension in the muscle. I'm lifting up on this really heavy table. I can feel it in my muscles. There's tension there, but the length is not changing. Okay, that's isometric. Now, this is going on as we're sitting here, right? If you're pushing against a chair with your butt, or your legs are pushing against the floor, or you're leaning against there's isometric going on a lot, but there's isotonic going on all the time too. So both of these are equally valid. They're equally happening, and too much of isometric certainly can lead to excess stress on the bone. It can lead to like we talked about high heels last time. Heels are putting you in an isometric situation with the calf muscle. So it's in a state of contraction. The tension is there, but we're not getting any range of motion. There's no length change occurring. Okay, so anyway, the black and white of it, isotonic, the tone or tension remains the same, but the length of the muscle changes. We do get range of motion. Isometric, we don't get any length change, but we do see an increase in tension. Back in the 50s and 60s, there was a big push in the physical education world in schools, high schools, for isometrics was like the big deal. So they would have these guys like holding like a medicine ball and like just going up against the brick wall, or standing in a doorway and like pushing their arms out against the doorway, or holding and just holding and dangling and pulling on stuff. So that like kind of bulks up muscle, but it does a number on joints, and it minimizes range of motion, and it can create a lot of bulk, but not a lot in the way of range of motion. And we find that, again, range of motion, it really is beneficial for optimal blood flow and nerve flow and electrical flow.
Hey,
Hey,
so
Craig.
hey, what's going on, man?
Not much.
So, all right, I used to play football in high school,
Nice. Yeah.
and I used to get cramps, and my coach, this happens while I'm sleeping, and I'd wake up to it, and he just told me to point my shin to my knee, or my foot to my knee, my toes to my knee.
Oh, point your toes toward your face. So where
Yes.
you're getting the cramps
So
in your
where is
calf
that?
muscle?
Yes.
Yeah, he's right,
So what does
actually.
that have to do with?
Well,
Is that
even
slow
even
twitch?
even
No, it's
better
fast twitch.
for well, a couple of things. Um, oh yeah, football's all about being on the balls of the feet, right? I mean,
Yeah.
everything is on the balls of the feet. It's out in front of you, so you're kind of up. You're in what we call plantar flexion when you're doing football, and so you're in an isometric state. So you have like this subtle contraction when you kind of, it's like wearing a high heel, but we remove the heel and you stay in the same position as if you're like kind of on your tiptoes a little bit. And so, in football and running, right?
It
There's
would
so
feel
much
like an
running.
alien was popping out of my calf
Oh
muscle.
yeah, it's like throbbing and punching.
Yes,
Yeah,
absolutely.
absolutely. Yep, I can totally relate. So the idea is when you're in that isometric state, we have what's called an oxygen debt. And so when an oxygen debt occurs, we have what kicks in is a couple of things. What kicks in is anaerobic respiration, which means lactic acid builds up. And so you're going to have some of the soreness. But the other thing that's going on too is now that you're off your feet, it's that goes kind of back to that muscle memory, being nervous and muscle combined. You with football, with practices, and with you get what's like basically like an acute form of this muscle memory. So you're establishing muscle memory by strength training and by repetitive motions. And so the early stages of it, you're kind of establishing a muscle memory to be up on the balls of the feet. And it's a new position. It's more isometric. It's using up more oxygen, and to the point where it saturates, and now it needs it's not getting the oxygen it needs, so it triggers into using other sources, strictly glucose, to get the energy that it needs.
Well,
And so to get the energy the cells need. And so what happens is when you finally are relaxed, okay, you're finally relaxed, your muscle memory is still saying, I want to be in this mode. I want to be in contraction mode. And so that twitching is your muscles saying, wait a minute, we're used to being in this kind of mode. So the muscle twitch, you're getting what basically getting a twitch response. That's you're getting a hyper twitch going on to the point where it's the twitch hits what we call they call it treppy, and then wave summation, and ultimately leads to a cramp. And so and
like an
again,
alien.
like an alien, and it's truly too much electricity over and over and over to accommodate for what the muscle you're asking it to do. So you're asking the muscle to be contracted, you're asking it to be up on the balls of the feet. And so that nerve signal is saying, okay, I'm trying. And then finally I go home and I go to bed and I lay down and I'm off my feet. Well, the nerve signal is still doing this, and the muscle's still saying, yep, we still want to be in that mode. And so that's where you're getting that kind of, that those
Like,
action potentials go to the point where they just plateau out. And they call it tetanus. Have you heard? Like it's almost like a locked up muscle, like lockjaw. But that's an actual normal phenomenon called tetany, tetany, tetany. And so I'm going to kind of put on the brakes because in advanced, we do a PhysioX, kind of a virtual lab, even in face-to-face, when we do face-to-face advanced A&P labs, we still do some virtual labs together. They're called lab simulations. And we do about 4 or 5 neuromuscular simulations that discuss exactly what we're talking about. An action potential comes in, we get a muscle response. Well, what happens when multiple action potentials start accumulating, and we keep getting these twitch responses to the point where they almost hit like the wall. And so instead of being able to go through what we call a refractory period, they kind of hit this and they never get to go back down, and so they stay up in this it's like treppy is like their steps, and these steps of action potentials can lead to the wavelengths summing together and becoming a tetany state, which is like which is basically like a muscle contract, a cramp. So yeah, excellent question. Yeah, I played football too. I was a catcher in baseball for 16 years, and then
So was I.
I was a lineman in football for seventh, eighth, ninth, for 4 years. So, oh, you
I don't
played.
want to hold the other students
Well,
hostage
we're
here on
almost
the
done.
question.
So that's it. So there's your muscle work questions. Yeah, that's hurt. Plus, was it during high school too?
I still get it every now and then.
Sure. Well, you're on your feet a
Not as
lot.
bad. Not as bad though.
I want to tell
But I
all of
wake up and I
okay.
just remember,
More you need
toes to face.
toes to face. You can even what I have our patients do is I have them stand on a step or a stair, and then you just dangle your heels down.
Yep.
So it's the same principle. Or you can take a belt or something and put it down at your toes, and you can kind of pull them that
Sounds
way.
kind of extra.
Yeah.
But
Or here's a really good one. This one's so easy. Walk right up to a wall and push on the wall, and then put
do
your
calf
foot
muscles
back, and
exercises.
try to get your heel down to the ground, and you can just feel that stretch going.
Yeah.
You may want
Alrighty.
to increase magnesium and potassium content.
That's why,
That'll help.
he said you gotta eat more bananas.
Well, that helps. You know what has more potassium than bananas? No joke, and I'm not being funny. A bag of Lay's potato chips honestly has more potassium than a banana. Potatoes in general, especially sweet potatoes, have the highest amount of potassium. Bananas get all the credit. They're actually, I think the banana lobby must have really got heavy
Good
back
marketing.
in the 80s. Yeah, and really, got us. They took over that potassium corner of that market. But honestly, and nowadays too, a bag of Lay's potato chips, just the yellow bag of Lay's, if you look at the ingredients, they're only going to be 3: potatoes, salt, and oil. That's it. They've gotten rid of all of these long additives and preservatives. Now, not all chips have, but anyway, look at the amount of potassium in there. Look at the amount of potassium in a banana. And so anyway,
Sweet
go buy a bag of
potatoes you
Lay's.
mentioned, right?
Yeah. Oh, those are the best. Just go buy sweet potatoes, set the oven
Yeah, I
to
love 'em.
400, 375, even 350. Throw them in. You don't even have to poke holes in them. Some people, oh, you got to poke holes. No,
I poke holes. I'm a hole
you don't
poker.
you don't need to poke hole it. You can now a regular potato, maybe a sweet potato, just leave it alone. Seriously, just walk in. You don't have to walk. Just grab it off the shelf. Put that sucker right nowadays too. I'm seeing them; they're the size of footballs. You can put one of those in your oven, walk away, come back like an hour and a half later, pull that thing, it'll just squeeze right out of the shell and just boom. Man, that is as healthy of a food as you could get. That'll help with muscle cramps. But yeah, stretching, magnesium, potassium increase as well. And then stress. I don't know if you drink a lot of caffeine. Some folks I've had, some of my patients have had, they drink a lot of caffeine and sugars, and that agitates, especially their left calf muscle tends to be worse than the
Caffeine
right calf
affects
muscle. Yeah, especially
I do drink a lot.
Well, that could honestly that may help
That's
a little
the
bit.
culprit.
Yeah, restless leg syndrome, leg cramping at night. Often caffeine can be definitely a culprit for that, especially the left side.
You don't need
calf muscle.
caffeine to handle this class.
Well, you
Shoot.
do. I agree. You have to moderate though, or just accept. Just supplement all the caffeine excess with more magnesium and potassium, and then you'll be fine. And more water, drink more water to go with it. But I get it. You do need the
Absolutely.
caffeine. All right, this is about it. We're almost done for the night. This next slide gets into the fast twitch, slow twitch stuff, or slow twitch, fast twitch, type 1 and type 2 muscle fibers. There's a table in your portfolio you're going to have to fill out. And you only need to do 5 comparisons. You can, that's all you need. This one has a couple extras, but we're going to look at muscle fiber types. This also in the slide, notice my little finger bloop, it lights up when I hit the title. This is actually a hyperlink to a YouTube video that discusses this. The same YouTube video is in the Padlet. There's also a link to the YouTube video in your portfolio. So regardless, you have plenty of ways to get to this. I looked quite a few different spots. I had and this one is very good. I think it was from Khan Academy. They're excellent, but this gives a very just straightforward look at muscle fiber types. So we see what are called type 1 and type 2 fibers. And these are in all of us. All of our muscles are going to be slightly different from spot to spot. Now, certain people may have a higher abundance of a certain type of muscle as well. Some of that's based on your family history and genetics. Some folks train specific muscle groups or types to be more slow twitch or fast twitch, depending on what type of activity they're trying to excel at. But the type 1s we'll do first. These are the slow twitch fibers. They're going to come across as being a darker, deeper red color to them. They use a lot more oxygen. So whenever we see red, we're thinking blood is involved. Okay, red is blood. So more blood means more oxygen. So we would think of aerobics, right? Aerobic means with oxygen. So all of these have to do with the type 1 muscle fibers. Red, meaning lots of blood. Slow, contraction speed. Slow twitch regarding the electrical response. Okay. Aerobic, meaning the types of activity. Again, more long distance. If you run on the treadmill, if you're doing the elliptical, if you're doing swimming, bicycling, you're doing more aerobic, slow twitch training. You can last longer doing these types of training. So this is more your cardio workouts. They're it says resistant to fatigue. Well, relative to the other ones, they are. All right. So again, duration, fatigue, and these muscles generally, again, they're a lot stronger typically as well. So we would think of generally as like the legs. So when we think about chicken, we think of the thighs and the legs as being the dark meat, and that's chickens are well, they should be, unless they're cooped up, right? In a coop, those some folks that live in cities are allowed to have chickens, but there are restrictions, and so they have to be in this tiny little coop, and they don't really get any exercise. Well, we're not really talking about those chickens. We're talking about just normal chickens that have the ability to run around and be chickens, right? Well, they don't do a lot of flying, right? Chickens don't do a lot of that, but they do a lot of walking. They do a lot of running. They do a lot of different aerobic kind of activity. So the thigh meat, the leg meat, that's going to be your dark meat. It's usually a little, maybe a little greasier as well. Again, that the amount of activity can determine that as well. So you want a free range chicken if you're going to be eating chickens. All right. So type 2, and these are also the marathon runners, those folks who run, they drive in and you see the little stickers, 16.1 or whatever, these stickers on people's cars, like, well, I don't know what that means. Those are marathons, half marathons, quarter marathons, things like that. These guys are adept at the slow twitch fibers. Type 2, and so they're usually not good at sprinting. Type 2 muscles are going to have white to them. They have less oxygen demand. These are what they call the fast twitch muscles. these are going to be your breast meat and your wings for the chicken. And again, you know, if you've ever watched chickens, yeah, they run around, and if they get startled, if they get, you know, something happens, you know, they flap their wings and they get a little bit tweaked out for a few minutes, and they can zoom away, and they don't really fly. They kind of coast and flap and make a scene. That's fast twitch, anaerobic. They can't do that for a very long period of time. Again, this would be like your sprinters. They 100-yard dash. They line up and they you know, they zoom at a fast rate. And anaerobic, they're not using very much oxygen to get this accomplished. Short duration, they fatigue extremely easily. If we say, all right, now go 200 meters or now go 400 meters, likely they'll be able to, but again, it does take training and time and muscle memory and establishing. But yeah, if you ask them a sprinter to run a 1600 or run a mile, you know, it's no different than asking a miler to run a sprint. You know, so two completely different muscle types. And again, these muscles can be trained; they can be adjusted as well. All right. So that takes us into muscles. We're just about done. I just want to talk about one thing here for a few minutes. I want to go back to slide 2. So we looked at the characteristics and functions of muscular tissue. Right. So the basic characteristics are we need some sort of irritability or excitability. We need some contractility. We need a little bit of some sort of elasticity or in the ability to elongate and stretch. So we need to be able to shorten and we need to be able to lengthen. We also need some electricity included in that skeletal muscle grouping. Okay, so extensibility, contractility, excitability. All right, a lot of abilities. Functions of muscle tissue, again, we're thinking movement, heat production, and posture. We looked at the organization of muscle tissue down to the tissue of muscles to the tissue level. We looked at the epimysium around the belly, and then the paramysium around the fascicles, and then the endomysium around the fibers. That's it for organizing the muscles to the tissue level. Different types of contractions. We looked at isometric, isotonic. We looked at eccentric and concentric as well under the isotonic group. And then we just finished looking at slow twitch and fast twitch, or type 1 and type 2 fibers. So that takes us really to 6.5, which we're going to do on Thursday. 6.6, I just want to discuss just a couple of things briefly with that, and then I want to let you guys go for the evening. So muscle action as attachments. Okay. So just a couple of things real quick, and then we'll conclude. Muscles are this is just kind of an all-encompassing, what can we expect when we look at specific muscles. So from now on, really, we're moving out of the tissue level, we're moving out of the cellular level. We're just looking at what is a general muscle. Okay. Salute, general muscle. Private parts reporting for duty, sir. Let's see. Absolutely. Okay, so size, right? We've got ranges from extremely tiny, almost micro scale, all the way up to massive. We've got a variety of different shapes. We've got broad, narrow, long, short, triangles, rhomboids, flat sheets, thick sheets. We've got parallel. We've got pennate. We've got fusiform. We've got, anyway, muscles come in all shapes and sizes. That's kind of the point. Again, we look at a cross section. We see bone and then some muscle surrounding the bone. And again, each of these is an individual muscle, and these individual muscles are all connected to one another via what we call fascia. Now, when we look at fiber arrangement of muscle, this is going to help us determine sometimes maybe the types of joint actions that we might get from the muscle. So we see the parallel fiber arrangement. We see a fairly similar kind of origin and insertion site. So we're going to get more or less kind of a unilateral or a uniaxial, I should say, kind of action with these. So when we talk about muscle attachment, we've touched on a little bit, but we have what are called origin and insertion. Okay, origin and insertion. Origin tendon is the tendon that is anchored to an immovable bone. The insertion tendon is going to be attached to the movable part. So, so when we look at some of these, and I don't want to get too caught up on fiber arrangement. This is just showing you, again, we've got a bunch of different shapes. So, so anyway, let's look at this muscle real quick here. We've got this broad origin site and this small insertion site. Movement or action of a muscle occurs when insertion moves towards origin. So this would be attached to like your upper arm. This would be attached to your sternum. And so the fiber direction, fibers are like puppet strings. So the puppet string is attached to the anchor, and then we come out to the movable part and we pull on the string, or we shorten the fiber and we produce some sort of action. So the broader the origin, the more variety of range of motion that we're going to get. So this happens to be the pec major, which attaches to the humerus up toward the shoulder joint. So the pec major can do all kinds of different actions, very broad origin. We see a similar thing with the deltoid, a lot of fiber directions going down and kind of coming to one spot. We can get a lot of actions going with the deltoid. So anyway, just FYI regarding fiber arrangement, not a big deal. I do want to mention these. I just did a few minutes ago, but at the black and white of it is origin. Tendon is where the tendon attaches to an anchor or more or less kind of the immovable part. And then the insertion tendon. So oftentimes origin is going to be more proximal, and then insertion is going to be more distal. Insertion moves towards origin. So the insertion bone is going to move toward the origin bone. So when, for instance, when we look at this is what they call the brachialis muscle. It's kind of like the biceps muscle, but it's anchored or origin. Its anchor or origin is on the humerus, and its insertion is down here on the ulna. And action occurs when the muscle fibers shorten. And when I shorten this muscle, we're going to see the insertion bone move toward the origin bone. So again, think of these lines, these fibers as like puppet strings, and the origin is kind of where the puppet master is. The insertion is going down to the limb that's going to get moved. When I shorten or pull on the puppet string, it's going to create action and bring that bone closer to the origin. So that's what action is. Action is insertion moving toward origin. And again, these are tendons, origin tendon and insertion tendon. The muscle that's performing the action, the muscle that's fibers are shortening is called the prime mover. The prime mover is also known as the agonist. Okay, so the first two bullets here, in essence, are synonymous with one another. The prime mover for elbow flexion is the biceps or the brachialis muscle. Okay, for instance, the agonist and prime mover, it's the same thing. The fibers shorten. This is where action occurs or movement occurs. The antagonist is the muscle that lengthens during an action. So it's the opposite muscle to the prime mover. Prime mover shortens, creates the action. The antagonist lengthens during the action of the prime mover. So when we look at elbow flexion, the prime mover for elbow flexion is the biceps, At the same time, the antagonist is down here. The triceps are lengthening. So as I bend my elbow or create flexion at the elbow, my bicep is shortening, my triceps are lengthening. Now, vice versa, if I extend my elbows, now the tricep becomes the prime mover and it's shortening, and the bicep is now lengthening. It becomes the antagonist during elbow extension. So keep that in mind for Thursday when we look at muscles and muscle actions. Lastly, we have what's called a synergist, and a synergist is going to be, in essence, a helper, right? Synergy is a connection, right? When there's synergy, there's a link. A synergist is a helper. And a synergist sometimes helps the origin spot. So sometimes a synergist will kind of stabilize an origin. Sometimes a synergist, so that's what they call a fixator, that last bullet. A fixator muscle is a synergist type that's going to kind of stabilize the origin. Um, the A synergist can also assist with the insertion area. So a synergist sometimes is also kind of the secondary mover. So if I have a prime mover for a certain joint action, maybe I need a little extra help to get that movement to occur. So then I have a secondary mover or a synergist that will kind of assist and contract as well. So this last slide that we're going to see tonight shows us again with elbow flexion. We've got the prime mover being the brachialis, and then the antagonist, so it's shortening, and then the antagonist being the triceps, which is lengthening or relaxing. Now, a similar scene going on here. We've got the prime mover being the brachialis. This time it shows us two synergists as well. So the antagonist is still going to be there. They just removed it since they showed it over here. We have a synergist that's going to anchor help to anchor the origin. The deltoid anchors on the scapula, primarily the spine and acromion, and then it inserts down here on the humerus, kind of near where the origin of the prime mover, the brachialis, is. So basically what this synergist is doing on the proximal area, it's fixating or stabilizing the the humerus. So when the brachialis contracts or shortens, we don't get any type of compromise. We don't compromise the shoulder joint. So this deltoid can kind of stabilize the whole shoulder compartment. In fact, in my days in the clinic of shoulder socket injuries, whether it's a dislocation or subluxation, oftentimes it occurred when the patient was lifting or moving something. So their prime mover, the bicep, or maybe it was a tricep, something was fine, but they didn't have that synergist fixating and stabilizing the socket. And so so they would go to lift something that was a lot heavier, or they would lift something and they would get a shift in the weight of whatever they were lifting. And so the fixator wasn't quite ready to keep that shoulder stabilized, and so you'd get like an action that didn't have a stabilized humerus and thus stabilized shoulder joint, and so you'd get a dislocation or subluxation typically. But another type of synergist is just simply going to help at the insertion site. So that's what we see with the pronator teres. That's a small muscle kind of buried in here that helps with pronation, or helps with this action. So we can get that, kind of can help the bicep up. If it shortens a little bit, it takes some of the strain off of the brachialis or the biceps. Brachii. So anyway, that's pretty much it. When we look at muscle names, this is your last kind of your segue from tonight into Thursday. When we look at how muscles are named, they're named for, in many ways. We're going to see them named for shape, named for size, named for location, named for their action, named for how many origin heads they have, named for fiber direction. Anyway, we're going to see all kinds of naming techniques used. So sometimes it helps, sometimes it doesn't when we're looking at muscles, but just keep in mind between now and Thursday, if you're looking through muscle names, that's something you'll maybe kind of pay attention to, is the muscle name may give you some clues as to either what it does or where it's located. Sometimes where it's located gives you a clue to what it does. So anyhow, that's it. So Thursday we'll start here with an overview of musculature and